Okay. What's up, everybody? Today we'll be doing dance moves from the January contest. I think this contest was actually kind of easy, but hopefully we'll go through it pretty well or smoothly. So the idea is they're like a bunch of cows in a number line, right? So I'm gonna name them like 1, 2, 3, 4, 5 because it's just much easier. And so what happens is, right, there are going to be case swaps. And so, every second, right, 2 cow swaps. So the first swap is 1 and 3, I think. So this is going to change to this. Right, the next one is 1 and 2. And so position 1 and position 2 are going to swap. So now it's going to be 2, 3, 1, 4, 5. And let's see, I think what was after that? 2 and 3, 2 and 3, 2 and 3. 2, 3, 1. So it's these two guys. 2, 1, 3, 4, 5. And the swap positions, I'll keep on doing it till it ends, which is right here, 2 and 4. Why do I keep pulling up my code? Kind of an idiot. Okay. So please move. Okay. So 2 and 4. And this is what it ends up with. So, yeah. And your goal is that, like, let's say these cows move, like, infinitely or indefinitely. Count the number of positions the cow meets, right? So, and the answer says that 1 will reach 4 positions, 3 will reach 3, and 5 will reach only 1. So, yeah, you can see kind of a pattern. You'll notice that 5 is in its own kind of, like, cycle. 3 is, well, yeah. So 1, 2, and 4 kind of have their own cycle as well. And then 3 is kind of an odd case. 3 does move around. It's not like 5 that it's just like going to the same index every time. But every time there's k cycles, 3 will just go back to this guy. So yeah. So how would this work? So how do you find the amount of positions indefinitely, right? There's no bound. So maybe like you would think of brute forcing it, doing it like maybe k to the 100th time, 100 to the k time. I don't think that would work. Well, yeah, it won't work because n is 10 to the 5th, so it would have to be even slower than that. But yeah. So the idea is, the solution is, oh, well, actually, let's try to identify a pattern, right? So for now, within k swaps, let's just see how many positions each one reaches. So 1 reaches 4 positions. Right. 2 reaches, let's see, 1, 2 positions. 3 reaches 3 positions. And 4 reaches 2 positions. And 5 is just the same position, 5. So, what's the pattern? Well, let's just check the answer real quick. Like, look at the answer. So, 1, 2, and 4 appear to have the same amount, and 3 is just kind of an oddball, and 5 never moves. Okay. Well, if you notice, right, 3 lands on the same spot after k swaps. So, like, after k swaps, 2 becomes the new 1, 4 becomes the new 2, 3 becomes the same 3, and then that. And you'll notice that, like, every time you do k swaps, this ending kind of permutation changes. They kind of swap around, and in the end, when they go through another k swaps, it's going to go as if it's going to go through the same order, like in that kind of fashion. So 2 becomes the new 1, 4 becomes the new 2, this becomes the new 4, 1 becomes the new 4. And they keep swapping around. So, yeah. So one thing I noticed is that since 3 ends on 3 after k swaps, that means it will only reach the amount of positions that happens in the first k iterations. Because it always ends on 3, and then 3 will go to 1, and then 1 will go to 2, or 3 will go to 2 from here, these two. And then 2 will go back to 3. Or, I mean, then it will go back to 3. So it always goes to that same amount. Like, if you just imagine like a graph, if you just track what 3 goes through, 3 goes here, and then lands back on 3. Since it lands back on 3, we know that it will go through the same direction every time. The same, yeah. So 3, we know that it would stay the same after k iterations. 5 will also stay the same because it also lands on the same position, but it's kind of easy because it never really moves. But okay, so now the question is, what about 1, 2, and 4, right? So you'll notice that 1, 2, and 4 kind of land in a cycle. So 2, if you kind of make like if you iterate through the cycle in a fashion like this, so 2 goes to index 2, which is 4. So this arrow will point to index 4, which lands on 1, and 1 lands on back to 2, and then it goes into a cycle like that. So if you do a cycle with just like indexes, you'll notice that they all have the exact same amount of positions, because since they have since they have a cycle within indexes, they're gonna have like so like the next k iterations, what's gonna change is that, let's say 2 goes here, I think, because 1 lands on position 4, in this case 2. 2 lands on position 1, so 4 is going to end up here. 3 and 5 are going to stay the same, and 1 will be here, right? Because position 4 lands here. So yeah, it's going to land here, and remember, these guys are the cycle guys, and it will keep on going, and then after another k iterations, it will land back at 1, 2, 3, 4. So only like these guys, like the people in the cycle, they will exchange exchange indices, and when you go infinitely, they're gonna all have the same amount of possible indices that they can land on. If that makes sense. Yeah, that cycles are always kind of hard to explain. So what you can do to calculate all possible cycles is just union these sets. So I kind of drew it in set notation for a reason. And so basically this one box is going to represent this. And so basically you kind of just union between two sets. And you take in this case, it would be, since 1 and 2 are both in these, so it would be 1, 2, 3, 4 actually. Because yeah, if you don't know what union is, it's like if two sets have the same like number in it, it will only count to it once. But if they have a new number, it will add to the set. That makes sense. So yeah, that's 1, 2, 3, 4. And then so knowing this, the union of all of these, all these sets are going to be this, like, have the same amount of positions, or the same amount of positions reached, because they're all in the cycle and they can all swap interchangeably at any point. So yeah, that's kind of how it works. So okay, let's just move on to the code, I guess, because it's a little hard to explain. I think cycles are kind of stupidly hard for beginners, but yeah. So I'm gonna have a group of sets, a vector of sets. So this is just a dynamic array of sets. Yeah, and then I have my numbers, and so I'm gonna make this 0-base index. So in this case, for 5, it would be 0, 1, 2, 3, 4. And I'm making a 0 index because it's just easier. I insert all these to the set. So this set is going to represent how many positions a person has reached, or indice has reached. And then this way, I'm going to this is the exact same thing as this. It's just I swapped it. So B A. So what's going to happen is since the value of the indice can change, right? Because they can change. So this is not 1 anymore. This is 3. What can happen is you just plug in this number that's in the this vector describes what the array is currently like. So maybe after one change, I think the first one was 1 and 3, so it just changes like this, right? This describes so the vector describes what value the position a minus 1 is on. I remember it's 1 base index, that's why I have to minus 1. And then I insert the new position, which is b, right? So we go back to this example, right? Vector a minus 1, so a minus 1, like in the first case it's 1 and 3, right? Subtract 1 is 0, so take 0. And so it takes the position 0 and then inserts the new position that it reaches, which is 2, right? And then it will keep on doing that for the first k iterations. And the reason for that is you just got to know where it moves after k iterations, because after k iterations it goes through the same pattern over and over again. Then you swap it just to keep it so that you know where the you can simulate it easily. Okay, this is just simulation. Actually, I just said that earlier. Then I'll have a visited array. This will be helpful. So a lot of cycle problems you'll want to cycle through to detect cycles. I said cycle twice. So in this way, I'm going to, this kind of idea is same represents all the indices that are in the same cycle. And so I'm just going to loop through all of them. I'm going to count their visited, right? So I don't, so I count visited, right? And remember, you can't have crazy cycles where where I'm just going to make it like a graph. 3 points directed to 1, 2, and 4. Like in the problem swappity swap, if you're aware of that. That was kind of a while ago. But let's say this is its own cycle. You can't have an outside cycle because you're going to be swapping. If you're swapping 2 positions, I think if you're swapping 2 positions, it's almost impossible to do it that way. It's the only way to have an outside part of the cycle is if you end on k, like this, or end on your same position, because swapping, this is going to be hard. Hopefully y'all understand. But I'm going to keep a same array, so these represent all the numbers in the same cycle. And then I'm going to have a set, so I'm going to keep track within every single, this is just union. I'm just going to union all the possible positions into one big set. And then I assign every single person with the same, in the same, vector. So within the array of positions in the cycle, I'm just going to assign all of them to the same size. And the size is just the amount of positions it reaches. And then at the end, I just output ands. So yeah, basically, in summary, it kind of just goes through every single cycle. So if there's multiple cycles, it'll treat them separately. And and then it unions all the same, all the positions in the cycle. So 1, 2, and 4 is one cycle, so it union 1, 2, and 4. 3 is its own cycle, so it only unions 3. 5 is its own cycle, and you only unions 5. So yeah. Complexity wise, I would say this is about, let's see. I think the graph may be annoying. I think I had a memory limit exceeded, which is kind of funny because I did 2 graphs, which you should never do. think complexity-wise, I would like to say it's O of n because you're traveling every position once. Oh, but here, okay, this is kind of stupid. I looped through all of it, so, and then this is logarithmic every time. I may not want to bother with it. I don't know. I think it's log n log n. Could be. I think it is log n or n log n. Let me just check out the solution real quick. N plus k. Oh, okay. He did something different. He used DFS for some reason. Oh, he just DFS'd the different possible people in the cycle. Oh, mine's very similar to this guy's. Daniel's or Mittal's. He's a pretty smart dude. He's just did it Java. Yeah, so he went through the cycle and then he added his things into the cycle into a set. Yeah. I guess it's O of n plus k. So yeah. I think that'll be it for today. This one was kind of interesting. I liked it a lot. I would like to say though, like if you want to get good at functional graphs and like cycle detection and stuff like that, you just practice. I think Codeforces has a lot of good places to start. But yeah, this is I'm not really a big fan of functional graphs because they're pretty tough. Like especially when I was a beginner, I still am a beginner technically, but it's pretty tough.